kind of just reinforce what we covered in lab Thursday. And I do have handouts for our Thursday's lab. And one of those handouts is if you do it, you get lab credit. So if you watch the videos and do that, you could get lab credit, but you don't need it because you can drop a lab. So does that make sense? And then Monday, we're going to be ready then for part 7. Okay. So this, I like it when things in chemistry make sense. This totally makes sense. So we can use the JAG to separate our metals from our nonmetals, and metals are going to lose electrons or so to become cations, and nonmetals are going to pick up electrons to become anions. And so the cation, you figure that's the metal that loses an electron, will always be smaller because it lost an electron. As it turns out, I think we talked about this before. This is the one that works. Okay, the structure of an atom, we have, this is the nucleus. We have protons and neutrons in here. We'll go ahead and make that a lithium. I know it's got 3 protons. We'll go ahead and get it 3 neutrons. We'll give it 3 electrons. Electron, electron, and electron. Kind of buzzing inside here. Actually, it's the electron that gives the volume of any atom. So if you have a cation that loses an electron or so, okay, it becomes smaller compared to the atom it was before. If we have a nonmetal that picks up electrons, it becomes bigger. Okay, so anions are bigger than the neutral atom. So aluminum is a metal. Aluminum is right here. We said that those 3A metals will lose all of their 3 valence electrons, become +3 charge. So here we have neutral aluminum. These are in picometers. I love picometers. These are in picometers, 118 picometers. It loses 3 electrons at 68 picometers. Makes sense. It loses 3 electrons. If we compare that to sulfur, now sulfur is a nonmetal. Sulfur is going to pick up 2 electrons to become like argon. It'll have the heart of a sulfur atom, but the electrons of an argon atom, basically. So it becomes a -2 charge. So here we can see that it gets bigger. I love it. It makes sense. We still need to go back and pick up part 3, which is the sizes of just plain old atoms without any charges. And we will do that. But whether it's the size of an atom or a size of an ion, it's a balance between attractive forces and repulsive forces. So if this is our atom, the attractive forces would be right here. The oppositely charged things attract. So it would be like that. That's my attractive force. Okay. So if those get stronger, my atom or ion is going to get smaller. The repulsive forces are right here. So if like repulses like, let's just put it that way. So these electrons are repulsing each other. So if our repulsive forces increase, it's going to get bigger. If our attractive forces increase, it's going to get smaller. So you kind of have that balance that's going on. If repulsive forces are increased, okay, then it's going to get bigger. If repulsive forces are decreased, it's going to get smaller. So you see the JAG here. These are our metals, kind of gold metals over here. And I guess they're all gold, aren't they? And over here we have our gold nonmetals. But you can see the blue things are the things that have lost electrons, that are positively charged cations. And for everyone, if you were to evaluate it, you're going to see that the cation is always smaller than the neutral atom. And then over here for our nonmetals, you can see that the anion is always larger than its neutral parent. To me, it makes sense. So it seems like forever ago, but the other day when we met, we talked about things losing electrons and picking up electrons. The metals will lose electrons, the nonmetals will pick up electrons, all to get like the rare gas. So remember the way this works, and we'll go ahead and pick on these guys, is oxygen and fluorine will pick up, this will pick up 2 electrons, fluorine will pick up 1 electron to get the 10 electrons. If you go, and this is period what, period 2? If you go into period 3, and this slide is kind of picking on these guys, sodium and magnesium, they're actually going to kick off 1 electron. Sodium will kick off 1 electron instead of 11 electrons, now it has 10 electrons. Magnesium will pick off 2 electrons, so instead of 10 electrons, instead of 12 electrons, it will have 10 electrons. Those are what we call isoelectronic. So The O2 minus, the F minus 1, the Na plus 1, and the Mg plus 2, they are all isoelectronic with neon. Isoelectronic. They all have the same 10 electrons configured the same way. Well, if we were to look at sizes not of the neutral atoms, but sizes of the ions, it might kind of surprise you, because you might be like, well, I'm sure sodium and magnesium is going to be bigger because they've got more protons in their nucleus. But if we kind of evaluate it, in the nucleus of the oxide anion, the O2 minus, it has 8 protons because it's atomic number 8. Fluorine has 9 protons, atomic number 9. Sodium has 11 protons, atomic number 11. Magnesium has 12 protons, atomic number 12. So, and I can't find my pen this morning. Goodness gracious. I know, I bet I left it out. What I wanted to do was, I think I've tried this before. This doesn't work, does it? Nope. Ooh. Does this work? Nope. What I wanted to do was to draw a little, over here, I want to write 10 electrons. Why? Because they all have 10 electrons. They're all isoelectronic. And then of these 10 electrons, let's look at how they're being drawn to the nucleus. So we have these 10 electrons being drawn to a positive 12. 10 electrons being drawn to a positive 11. 10 electrons being drawn to a positive 9 to a positive 8. As far as attractive forces, this guy's got it going on. Okay? So actually, as it turns out on the next slide, you're going to see the magnesium cation is the smallest of them all. It's got the most attractive forces. Smallest to largest. Magnesium cation, sodium cation, fluoride anion, and oxide anion. All right, and this is to kind of prove you, these are the picometers, picometers. Okay, so something that goes along with this whole formation of ions is ionization energy and electron affinity, and they're kind of like yin and yang. We'll start with ionization energy. There are all sorts of different types of energies. There's breaking energy, putting together energy, and in the word, it makes sense. This is to basically create an ion. So this would be removing how easy it is or how hard it is to remove an electron. And it's expressed in amount of energy per mole of electrons that you're able to take away. So if you're taking an atom and you're pumping it with energy to kick off an electron, which sort of atoms want to do that? Well, we said that metals want to kick off electrons, so they're going to have relatively low ionization energies. Non-metals, they don't want to kick off electrons, they want to bring in electrons. So we're going to see that they have high ionization energies. So if these are all, endothermic. These are all endothermic. They'll all be positive. So if you have a low ionization energy, it means, it's the one to kick off an electron anyway. Okay? It wanted to form a cation. Metals generally want to do that. Non-metals don't want to. These guys want to hold on to all their electrons and gain a few more to get the rare gas in the period in front of them. So I think we looked at another trend. We looked at electronegativity, which this is different. But so ionization energy has the same trend as electronegativity. It increases for group A elements, and you can see there are some exceptions. But you're going to see from element to element, ionization energy increases. Not so surprising, the closer you get, or the farther you get from metals into non-metals, it gets harder to strip off an electron. Makes sense. Within the group, it increases as you go up. And this is kind of showing that to you, where along the y-axis we have ionization energy, and on the x-axis we have atomic number. So you kind of see the periods. Of course, what do helium, neon, argon, krypton, xenon, and radon have in common? They're all rare gases. So relatively speaking, they definitely don't want to have an electron stripped off. They're like, dude, I got an octet. What are you doing here? Take away an electron. So these are ionization energies of some elements. And you can see how these are lower. These would be our metals. And here's our non-metals. Different ways to look at ionization energies. This one is just trying to show you in the second period where it's easier to kick off that 1 valence electron, 2 valence electrons of beryllium, the 3 valence electrons of boron. Then when you get to carbon, 4 valence electrons, you're like, dude, should I kick off these 4 or should I bring in 4 more? 1, 2, 3, 4 to get a complete octet. And nitrogen, so it just wants 3 more to get a complete octet. That's why it's -3. And oxygen only wants to take in, not kick them off. So ionization energy is higher for those nonmetals. So here's the deal, though. Once you kick off 1 electron, you can go for the second one. So there's first ionization energy, and then there's second ionization energy. So for instance, if we pick on magnesium, magnesium wants to form a +2 charge. You're going to kick off 1 electron, and then you're going to kick off another electron. First ionization energy, second ionization. And as it turns out, now we're going to pick on magnesium here in a minute, but you're going to see that the first one is easier to go, and the second one's harder. The third one will be even harder, the fourth one will be even harder. So subsequently, once you have a cation, it gets harder and harder to strip off 1 more. So it looks like this. IE stands for ionization energy. The first one's the lowest, then the second one, the third one, they just keep getting bigger. So let's pick on magnesium, and I've got a few videos to kind of show you what that would look like. Magnesium has 12 electrons, and this is how those 12 electrons are configured. You can kind of see the core electrons in the 1s2, 2s2, 2p6. That would be like the 10 electrons like argon. The 2 electrons that are going to go are the valence electrons in the highest end. Of course, n is equal to 3 is the highest end. Those are the 2 electrons that are going to go. We can kind of look at the ionization like this, where we take a neutral magnesium atom, we zap it with ionization energy as kind of the 2 reactants. On the product side, we end up with an Ng +1 and 1 electron. So here's a video to kind of show you what that looks like. Tipping point, when we look at ionization energies, I have a table to show you, but we're going to see where it's comfortable if you're dealing with metals anyway. Whenever it's already comfortable, it has a complete octet, it's that next one, that tipping point that goes, whoa. There's a big break between the second and the third ionization energy for magnesium because it was happy after the second ionization energy. All right, so here's the table I was talking about. These are all in the same period. So this is all period 3. Okay, so sodium forms a +1, magnesium a +2, aluminum a +3. Silicon actually is in the same column or group as carbon. It goes a ±4. You can't hang your hat on what it does. Phosphorus is a -3, sulfur is a -2, chlorine is a -1. Of course, argon doesn't form any charge. So I mentioned the tipping point. The tipping point for sodium would be between its first and its second ionization energy because it's totally cool with when it's a +1 cation. Magnesium, we saw something like this, the tipping point. Aluminum, the tipping point comes down here. Silicon. Now, when we go over to phosphorus, sulfur, chlorine, and argon, recognize that ionization energy is a weird thing for them because they don't want to lose any electrons. They don't want to be a cation. So already, like you can see, I'll just show off this. Already you can see that sulfur is, to get off 1 electron, sorry, I'll go across here. Phosphorus, already to get off the first electron, you're looking at about twice that as to give off the first electron of magnesium. Okay, so we have ionization energy and we have electron affinity. Ionization energy is kind of for the metals, like you kick off an electron. Electron affinity is kind of for the nonmetals. You basically bring in electrons. So if the person has an affinity, such as myself, for chocolate, that means they love it, love it, love it, love it. Okay? So electron affinity must love electrons. And who loves electrons? These nonmetals. So we're gonna see that actually for some of these, it's not endothermic, it's actually exothermic. So we have to kind of remember what we know about that. Endothermic, we use positive delta H's, and exothermic, we're negative. So dang, if you get charged from eating chocolate, you're going to give up energy when you get these electrons to chocolate. And that's what we're going to see with the nonmetals. So if the energy change is negative, negative delta H, that means that actually energy is released, and it's a happy sort of species. If the energy is positive, that means you had to work. Okay, that's endothermic. So exothermic and endothermic. So got some arrows again. Again, just limiting it to the group A elements. So remember what the group A elements, you take these 2 columns and these 6 columns and you squish them together. And we kind of generally have this trend, although there are some exceptions, that electron affinity increases and electron affinity increases. So you're like, that's the same trend as the ionization energy. You're right. Same trend as electronegativity. Because electron affinity can be thought of as an atom's want for electrons. And who wants electrons most? These guys over here. So relatively speaking, metals have low electron affinities, and nonmetals have high electron affinities. So this is where I'm hoping you kind of remember what we know about delta H's. If they're negative, that's actually exothermic. And that must be a happy, shiny sort of anion when electrons are added to it. If your delta H's are positive, then it must have been endothermic, had to put energy in to go ahead and make it accept electrons. So here are some, so these are delta H's, change in enthalpies, EAs, associated with electron affinity. Negative, that means heavy. Positive means it had to work to add those electrons. So we can kind of see here are some electron affinities. They're not as negative as these. Interesting. Mixed bag, is what it seems like to me. Not the prettiest trend I've seen. This again is how the electrons are configured, kind of the tipping point between metals and nonmetals. Boron is kind of almost a metalloid, but we definitely have lithium and beryllium, I guess, and boron. Easy to kick off electrons. Even with carbon, especially nitrogen and oxygen, they're like, dude, go ahead and give me a few more electrons and I'll get that complete octet. So they have high electron affinities. All right. Oh, I must talk like a banshee. So anyway, that's as far as I wanted to get. Dun, dun, dun. I don't know why this one's in there.